So in this problem, we want to know if there's a linear relationship between temperature, more specifically the high temperature on a particular day, and the price of lemonade at the local grocery store. So here's the data from 6 randomly selected days. We have the temperature, 43, 102, 74, and so on, and then the price of frozen lemonade on those particular days. Also done the summations here. So just as an overview, we're going to first plot and visually inspect the data. We're going to compute descriptive statistics, sample mean, sample standard deviation, sample covariance, and sample correlation. We're going to use hypothesis testing to answer the question, is there a linear relationship? Of course, we're going to first relate that to the plot we've already got there. Then we'll do a formal hypothesis test. We'll write an equation for the regression line. And for x values in the range, we will predict y. Then we will compute and interpret r squared, the coefficient of determination. So here's just a plot of the data, and it does look like there's a linear relationship. Looks like the slope is about 0.0035, and the intercept is about 80. So now we'll compute descriptive statistics. I already had those sums there, and there were sample sizes of 6, so we can get the sample means easily enough. The deviations for both the x's and the y's. And then I multiplied those deviations to get the cross products. So minus 25 times minus 0.01 is 0.25, and so on. Then I have the sum of the cross products is 12.61. You could also note that the sums of the deviations for both x and y are 0, as it should be. So I take the sum of those cross products, the 12.61, divide by n minus 1, and I get a covariance of 2.522. So now I'm going to square and sum the deviations. So example for the x's, I take that minus 25, square it to get 625, do the same for all the other deviations, and sum them up to get 3418. And then for the y's, I take the minus 0.01, square it, get 0.001, do that for all the other y deviations, and add them to get 0.0612. Then I can calculate the standard deviations by taking the square root of the sum of the squared deviation divided by n minus 1 for both the x's and the y's, to get a standard deviation for the x's of 26.15 and a standard deviation for the y's of 0.1106. Then I can calculate the correlation coefficient by taking the covariance and dividing that by the product of the two standard deviations, and end up with a correlation coefficient of 0.87, a strong positive correlation. For our formal hypothesis test, our research hypothesis is that there is a linear relationship. The population correlation coefficient is not equal to 0. And the null hypothesis is that there is not a linear relationship between x and y, or that the population correlation coefficient, rho, is equal to 0. So we get the critical value. Degrees of freedom is n minus 2, which is 6 minus 2, or 4. Two-tailed. From the t-table, we get a critical value of 2.776, so we're going to reject HO if the t-test is greater than 2.776 or less than minus 2.776. So we'll calculate r squared and then use that to calculate the standard error. So r squared is 0.87 squared, or 0.76. Then we'll take the square root of 1 minus r squared and divide by the degrees of freedom. And we get 0.245 for the standard error. Then the t-test is going to equal the sample correlation, the statistic, minus the hypothesized population correlation, which is 0, so I've left that out. So I just have r on the top, divided by the standard error. That comes out to be 3.55. Which is greater than the critical value. So we can conclude that we have compelling evidence to support the conclusion that there is a linear relationship between x and y. Again, I want to keep reiterating that that does not mean that x causes y. There could be another cause of both, or y could cause x. All we're doing here is some arithmetic. It's our theory that will tell us whether or not it's reasonable to conclude that x causes y. Okay, we're going to describe that linear relationship. We're going to calculate the slope and the y-intercept. Here are the formulas. Then for the slope, we take the covariance divided by the variance for the x's, and we get 0.0038. And the y-intercept, y bar minus the slope times x bar, we end up with an intercept of 0.742. And then we have our regression equation, the intercept plus the slope times x. We can use that to make predictions, at least within the range of our x's. So all of our observed values of x are between 34 and 102 degrees Fahrenheit. So we're not going to be able to use our regression line to predict what will happen when the temperature is minus 8 degrees Fahrenheit. So if x is 40, we can just plug in, and we would predict the lemonade price to be 0.90. But if x is 11, if it's 11 degrees outside, we're not going to make a prediction. It's not within the range of x's for which we have observations. So now we're going to compute and interpret the coefficient of determination, that is r squared. So of course we'll just square r to get r squared. What that means is that changes in temperature account for 76% of the changes in lemonade price, or more specifically, the variation in x values from their sample mean account for 76% of the variation in the y values from their sample mean. Just as a recap of what we just did.